So for part one of this question, we have to draw a diagram showing the forces acting on the girder. So I'm just going to add those forces to the existing diagram here. We know the mass of the girder is 20 tonnes, which means 20,000 kilograms, which means it has a weight of 20,000 G. We also know that acting on the girder will be a tension force here, which we're told is T, and we're told that the tension is equal in both of the ropes, so there's a tension force here as well. Now, part two, we've got to write down in terms of T the horizontal and vertical components of the tensions in the ropes acting at C and D. So if we look at C, we can see there's a tension force like this, acting at an angle 40 degrees. So if we think about the components, there's a horizontal component adjacent to the angle, which will be T cos 40 degrees. And there will be a vertical component opposite the angle, which will be T sine 40 degrees. Now, these two components will be the same for the tension acting at D. The horizontal component will be facing in the opposite direction, so this component here, T cos 40, but it will be of the same magnitude, and the vertical component will still be T sine 40. So we know that the girder is in equilibrium, which means that the forces acting on the girder must be balanced. And we can see that the horizontal forces acting are the horizontal components of the tension. So you have T cos 40 being balanced by T cos 40. So that won't tell us very much because they cancel each other out. But if we look at the vertical forces acting on the girder, we know that we have this component here and this component here, both of which are balanced by the weight. So that tells us I've got T sine 40 plus T sine 40 equals 20,000 G. And that tells me I've got 2T sine 40 equals 20,000 G, and I can use this to evaluate T. This gives me a value of T equal to 152,000 newtons approximately, so I can then round my answer to 152.5 kilonewtons by dividing by 1,000. Now, the forces acting on the ring at B, so there's going to be a tension acting upwards like that. We'll call this TA. And we also know that there must be an equal and opposite tension to the tension acting at C. So there's a tension T here and a tension T here. And of course, we know the value of those tensions, 152.5 kilonewtons. So to now calculate the tension in the rope AB, so there's B and there's A, we need to look at resolving vertically. So if you look at the original diagram here, if I draw in a vertical like that, the force we're looking at here, there's a tension there and there's a tension there. Now, I can use this angle here if I want to, which has got to be 50 degrees. And then you can see I've got a component of the tension acting downwards like that and a component acting to the left like that. And the same on the other side. I've got a component acting vertically downwards and a component acting across like that. The two horizontal components just cancel each other out. But what we know is that there must be a vertical component of the tension here and a vertical component of the tension here, both of which balance this upwards tension TA. Now, remember we said the angle was 50 degrees. In both cases. So we know that downwards we have T cos 50 plus another T cos 50. That's these two components here. And they must be balanced by upwards the other vertical force, which is TA. So I'm balancing my forces vertically here. So this then tells me that 2T cos 50 is equal to TA. And I'm going to use this value that we calculated for the tension earlier, and this tells me that TA equals 196,000 newtons, which you will notice is the same as 20,000 times 9.8. And that's because this essentially takes us to the answer to part 6. How could we have answered part 5 without any calculations? Well, if we treat the whole system as a single whole, then effectively the tensions in these ropes here and here would cancel out, leaving us with just the tension acting upwards here to be balanced by the weight acting downwards here. And because the system is in equilibrium, that means the tension in the rope AB would have to equal the weight of the girder, which is 20,000 G or 196,000 newtons if you use the value of G as 9.8. So question 3, a box of mass 8 kilograms is at rest on a horizontal floor. So if we think about forces acting, we have the weight acting downwards, 8G, and that's going to be counterbalanced by the normal reaction acting upwards like that. Part 1 asks us to calculate the value of this normal reaction, and that's going to have to equal the value of the weight because vertical forces must be balanced if the object is at rest on the floor, so 78.4 newtons. Now, in part 2, the box remains at rest on the floor, but a force of 15 newtons is applied to it at an angle of 35 degrees to the upward vertical. So we have a force of 15 newtons and the angle given 35 degrees like that. So we now need to draw a diagram showing all of the forces acting on the box. So I've added in the 15 Newton force at an angle of 35 degrees to the upward vertical. Now, I don't think the answer wants us to include the friction at the moment, but when the box has the 15 Newton force applied to it, its intended direction of motion is going to probably be towards the right. So friction would try and oppose that motion and would act in this direction over here. But we'll come to that in part 3. So in part 3, we have to calculate the new value of the normal reaction, also the frictional force. So I'm going to start off by looking at the vertical forces. So we now have to account for the component of the 15 Newton force that's upwards. So the 15 Newton force will have a component acting upwards like that and a component acting horizontally like that. So this means that we have the normal reaction upwards, we have this component of the 15 Newton force acting upwards, and then we have the weight 8G acting downwards. So that tells me that my normal reaction plus 15 cos 35, you can see that the vertical component is adjacent to the angle, they must be equal to 8G, and I can then rearrange this to evaluate my normal reaction, and that comes to 66.1127 ... so I'll round that to 66.1 newtons to 3 SF. Now, to calculate the friction, I need to look at the horizontal forces. So these must also be balanced because the object is at rest. So what do I have acting horizontally? Well, I have the friction acting to the left like that, and that's going to be counterbalanced by the horizontal component of the 15 Newton force. So that means that the friction must be equal to 15 sine 35, and if we evaluate that, that gives us an answer of 8.6036 ... or 8.60 newtons to 3 significant figures. So in question 4, we're not specifically told to draw the force diagram, but we need to draw the force diagram. Now, the first key piece of information is that the block has a weight of 75 newtons. So we're going to draw that in place. And because we're given the weight directly, not the mass, it's 75 newtons. It's not 75 kilograms. So the weight is 75 newtons, not 75 G. We're already given the weight, we don't need to calculate it. The plane is rough and inclined at 25 degrees to the horizontal, and it's in equilibrium, so the forces are balanced, and there's a horizontal force of 25 newtons acting as shown. So a couple of forces we need to add: the normal reaction force, which will be perpendicular to the slope at the point of contact, and also if the 25 Newton force is acting to basically hold the block up on the slope and attempt to push it up the slope. That means friction will be opposing that direction of motion, and friction will look like this. Now, we need to put in some components. So I'm going to put in the components of the 75 Newton weight. So I have a component like that and a component like that. And then we remember that this angle is always the same as the angle of the slope, so that's 25 degrees. And I also need to do the same for the 25 Newton force. So I put in a component of it that's perpendicular to the slope like that, and then a component that's parallel to the slope like that. And then the angle I can use again, this angle here, is 25 degrees, thinking about my alternate angles, or Z angles as some people like to call them. So we've got to calculate the size of the frictional force acting on the block. So we are going to balance our forces. I'm going to start off by balancing my forces parallel to the slope. So all the forces that go in this direction must be balanced. So if we look and see what we have here, I'm going to highlight things in a blue colour. I've got friction acting down the slope like that. And I've got this component here also acting down the slope. There's nothing else acting down the slope. So let's take this combination here. That means I've got friction plus 75 sine 25. You can see it's opposite. You can see this component here is opposite the 25-degree angle. And I know that they must be counterbalanced by the other parallel component, which is this one over here, this orange component of the 25 Newton force. Now that is adjacent to the angle, so that is going to be 25 cos 25. And this then allows me to work out the friction very easily straight away. Now, interestingly, when I do this, the friction comes out to be minus 9.03867. Now, there's no need to panic here. The frictions come out as negative. That doesn't really mean anything other than we've drawn the diagram and the friction should be in the opposing direction to the way we've drawn it. So the actual value of the friction is, of course, 9.038 ... So that would be 9.04 newtons. Now, for those of you worrying about well, why would the friction act up the slope? Well, it's going to be the case that the weight of the object is so heavy that effectively, even without the 25 Newton force aiming to push the object up the slope, the 75 newtons is such a large weight that the object is automatically going to try and roll down the slope, and so friction is effectively going to try and oppose that movement by being up the slope. So all that means is that the frictional force is actually acting upwards like that. It doesn't matter. If you get that negative value, that means the magnitude of the friction should be 9.04 newtons, but you have to think about the opposite direction that you actually drew the force in. And this happens sometimes when we draw a force diagram, we don't put a force in the correct direction, and all that happens is when we do the calculation, we end up with a negative answer, which tells us that our force should have been in the other direction originally. So question 5, we've got to calculate the size of the force F and the size of angle theta. So I'm going to draw in the components of F, and I've got a horizontal component like that and a vertical component like that. Now my horizontal component is F cos theta and my vertical component is F sine theta. Now, the object is in equilibrium, which means that the horizontal forces must be balanced. So horizontally, what do I have? I have this and I have this. They must balance each other out. So that tells me that F cos theta must equal 5. Now, vertically, if I look at the forces or components that I have this and this, one acting downwards, one acting upwards. They must balance each other as well. So F sine theta must equal 2. Now, there are lots of different ways in which you can solve this pair of simultaneous equations. I am going to do equation 2 divided by equation 1. So that then tells me I've got F sine theta over F cos theta equals 2/5. The F terms cancel, and of course sine theta over cos theta we should know is tan theta. So tan theta equals 2/5. This allows me to work out theta. and that equals 21.8014 ... so 21.8 degrees to 1 decimal place. But of course we don't use that rounded value in any calculations. We're going to use the fully unrounded value here and substitute that into either one of these two equations up here. So equation 1 then gives us f equals 5 over the cosine of theta, which equals 5.3851 ... or 5.39 newtons to 3 significant figures. So in question 6, what's interesting is that the rod and cables are of negligible mass, which means we do not have to take the mass of any of these into account. And we have a load which is suspended from the joint with a weight of 30 newtons. So I'm just going to draw in the weight of that load, 30 newtons here. So we've got to draw in a force diagram to show the forces acting on the load and the forces acting on the joint at A. So we have a tension here, which we'll call T, and the two forces acting on the load are consequently the tension and the 30 newtons its own weight. Now the forces acting on the joint at A, we've got an equal and opposite tension like that. And then we've got some kind of tension within the rod here. So that's going to be T, we'll call that TR. And then we're going to have another one, but inside the cable there. So we'll call that TC. So we could do this on two separate force diagrams. I've just added this to my original diagram for simplicity here. Part 2 asks us to calculate the forces in the rod and cable 1 and state whether they are in tension or compression. So the whole system is in equilibrium. So if we think about the load first of all, the vertical forces acting on that load must be balanced. And that's really helpful because that instantly tells us that T has got to equal 30 newtons. So we now know that force there. If we now think about point A and the joint, I'm going to draw that force diagram in a little bit more detail. So here's A, and we now know that acting at A, we've got a tension acting downwards, which is 30 newtons. So I'm just going to redraw this bit of the diagram in a bit more detail. I'm going to draw in a vertical line like that, and then that TC, let's draw that in again. Now, the angle here, which is the angle here, has got to be the same as 70 degrees. So again, you may want to think about that concept of alternate angles. If these two lines are parallel here, this line crosses them, you have what we call alternate angles. Sometimes people like to call them Z angles, colloquially. So that's in here, this is an angle of 70 degrees. Now the same thing down here, there's the force TR. So remember, this is point A. And again, we can draw in an angle, and this angle here, which is this angle here, is going to be 80 degrees. And again, you can use the same idea, the same concept that I've used previously. These two are parallel, there's the line in between them, so we get the creation of a pair of alternate angles, the 80 degrees marked, and then this 80 degrees here, and above we had the 70 degrees here. So we can now look at the forces acting on A very carefully. So let's take a look at components. So we've got a component of this TC force, which acts up like that, and then a horizontal component like that. And then we've got a component of the TR force, which acts downwards like that, and then across like that. Let's start by looking at balancing the vertical forces acting at A. So I'm going to balance the vertical forces at A. So upwards, I've got one component, and you can see it's over here. So this is going to be TC cos 70 acting upwards. Now that's got to be balanced by the component of TR acting downwards, which is here, and that's going to be TR cos 80. and we've also got 30 in there. And we can't really do very much more with that because there are two unknowns, TC and TR. Now, I'm going to look at the horizontal components, and what's interesting here is that if we look at the two horizontal components, I'm just going to highlight them so you can see exactly what I'm talking about. That's this component here and this component here. They're the only horizontal forces acting on A, but they're both pointing in the same direction. So really, if I were going to do this according to the way I've set up my diagram, then I've got this component up here, which is TC sine 70. Add this component here, which is TR sine 80. And that must equal 0, which is interesting in a minute because that means we're going to get a negative force. But that's absolutely fine. We're going to get one of these values. TC or TR is going to be negative, but that is not a problem, as I've mentioned in previous questions. So let's now have a look at solving this. So I'm going to take this result here and I'm going to rearrange it so it tells me that TC is equal to negative TR sine 80 all divided by sine 70. And then I'm going to substitute that in for the TC value over here. And that's going to tell me that negative TR sine 80 over sine 70 multiplied by cos 70 is equal to TR cos 80 plus 30. So I'm going to do a little bit of rearranging. So we've got negative TR sine 80 over sine 70 cos 70 minus TR cos 80 equals 30. And we then have to factorise TR here. So TR minus sine 80 over sine 70 cos 70 minus cos 80 equals 30. And then we divide 30 by the contents of this bracket here to give us the value of TR, which is going to be negative. We'll talk about that in a minute. So this then gives me TR equals minus 56.38155 ... and I'm going to store that in a calculator memory carefully so that I can use that in the calculation of TC. So if you remember the calculation for TC, we can then substitute back in our value of TR, and this then gives me a value of TC, which works out to be positive. And we'll revisit this in a second and think about what this actually means. So let's round these values. This tells me that TR is equal to 56.4 newtons. Take the positive value. So take the magnitude of that value. We'll explain the negative sign in just a second. And then TC is equal to 59.1 newtons, both given to 3 SF. So remember what these forces are. That's the tension in the rod, and this one's the tension in the cable. Now, to explain that negative result that we got, we're going to need to revisit the diagram. So if I now revisit the diagram, the cable tension was positive, which means we got the direction of the tension acting on A within the due to the cable as being correct. Now, this means that if I look at the cable in a bit more detail, there'll be equal and opposite forces within the cable. There'll be a force like that, which matches that TC, and there'll be a force like that inside the cable. So think about the difference here. This force that I'm about to circle, that's a force acting on the jointer A. And these two other green TC forces, they're forces within the cable. Now look at the direction of them. Look at what they're doing to that cable. They're pulling it. They are stretching it. So that tells us the cable is in tension. If you look at the forces inside the cable, they are stretching it outwards, so the cable is in tension. And if something is in tension, it will be pulled apart like that. So these two forces tell us the cable is in tension. Now, let's think about the tension in the rod. that came out to be negative. So that means that this force here acting on A, if you can just see me circle it there, we got the direction of that wrong. So if we actually look at what it should have looked like, if that's point A, that force acting on A should have been like that. It should have been in the opposite direction. If we now then look at the forces internal to the rod, inside the rod, there must be a TR force opposing the TR here that points in the opposite direction within the rod, and then there must be an equal and opposite force like that because the rod is in equilibrium. So the internal forces acting within the rod look like this. Now look at those two forces and think about what they're doing. They are pushing inwards on the rod. That means they are squeezing it inwards or compressing it. So that means the rod is in compression or thrust, as we sometimes call it, because the two forces acting within the rod, TR and TR, push inwards like this. So question 10, we have these 4 wires attached to the top of a telegraph pole, and the pole is in equilibrium with tensions in the wires as shown. So part 1 asks us to use perpendicular directions as shown in the diagram. So it's basically telling us to look at I and J components like that. And the 60 Newton force, let's draw in its components. It's going to have a horizontal component like that and a vertical component like that. So its horizontal component is positive and its vertical component is negative, acting downwards. So if we were to just look at the components independently, that would be 6 cos 75, and that 60 cos 75, this would be 60 sine 75, but as a vector, that would be positive 60 cos 75 and negative 60 sine 75. Now, if we evaluate these using our calculator, we know that 60 cos 75 is equal to, in its decimal format, not its third format, 15.529 dot dot dot. And then the vertical component is equal to minus 57.955 dot dot dot, which if we round that to 1 decimal place, that's 15.5 and minus 58.0 to 3 SF, or 1 decimal place. Now, part 2 says find T in both component form and magnitude direction form. So if we look at the tension force, we don't know the angle above the horizontal at which it's acting, so I'm going to call that theta. Now, what we do know is that all 4 forces add together to give a vector sum of 0 because this object is in equilibrium. So if we start by splitting them up, resolving them into their components, we can do this in vector form. So if I start with T first of all, that gives me T cos theta, T sine theta. And you can see both components, horizontal and vertical, are in the positive directions. Now, we then have, if we go anti-clockwise, this 60 Newton force, and we have its components already, 60 cos 75 minus 60 sine 75. And then I'm going to look at this 40 Newton force. So there's a component to the left like that and a component going down like that. So that's minus 40 cos 45 minus 40 sine 45. And then the 50 Newton force, we have a component to the left like that and a component upwards like that. I'm just going to clear a bit of space here. So that is minus 50 cos 30 and then 50 sine 30, which is upwards, so positive, and that must equal 0, 0. Now from here, this means I can read off all the information at the top and I can read off all the information from the bottom, and it's very easy to set up 2 equations, one that tells me what T cos theta is and one that tells me what T sine theta is. So using my calculator, I get T cos theta equals 56.05 dot dot dot, stored it in memory A, T sine theta equals 61.2 dot dot dot. And we've been here before in needing to solve equations of this nature. So I'm going to do equation B divided by equation A, and we've seen from previous work this will give us T sine theta over T cos theta, which just gives me tan theta. And tan theta must equal the value 1.092 dot dot dot, and I can then use inverse tan to find out that theta equals 47.530, I'm just going to store that in memory C so I can use that to work out what T is. Substitute into either one of these equations and use that to work out the value of T, and either of these equations will give you T equals 83.021 ... So we now have T in both its forms. If we want the tension in its vector form, well, that's T cos theta over T and T sine theta. So that's 56.1 as its I component and 61.2 to 3SF using these two values here. And if we want T in its magnitude and direction form, then we simply need to say that T is equal to 83.0 newtons, and it's at an angle of 47.5 degrees above the horizontal, reading from the positive x-axis in an anti-clockwise direction. Now, in the last part of the question, we replace T with a force that is 40/35. So we then are going to find the vector sum of the forces by adding them all together again. But this time, we're told that there is going to be a resultant force. So that means the pole cannot be in equilibrium. So I'm not going to set it equal to 0. I'm just going to put in those three other forces in their component form. So here they are, the three components, the three other forces in their component form, and we're now going to add together the components in the I direction and then the components in the J direction, and we're going to see what we get. And essentially, if it's not 0, 0, that means there is a resultant force. So I end up with these two values for the components. I've stored them both in a calculator memory. Now, to find the magnitude of this resultant force, remember we can use the modulus notation here. We take each of these components, ignore the negative signs because they won't be relevant in calculating the magnitudes, square them, add them together and square root. And this is where storing these in calculator memories makes it very easy, so we can use the full accuracy without having to worry about typing in lots of numbers. So this means the resultant force has a magnitude of 30.8 newtons to 3SF. Now for its direction, well, we need to draw in these components. So that's a component of minus 16.05 ... So that's going to the left, and then we have a component minus 26.23 going down like that, so that the angle here in this triangle, let's call that, we've already used the angle theta, so I'm going to call that angle x. So x is going to equal tan to the minus 1 of 26.23 ... over 16.05. There's no point using the negative signs here because we're not interested in using those. We just need the lengths of the sides of our right angle triangle, essentially doing a bit of basic trigonometry here. And again, having stored these values in calculator memories makes it very easy to work out that that angle is 58.5371, and I suspect that the angle that we will be required to give if we're measuring with the positive I direction is this angle here, which is taken in a clockwise direction. So if I do 180 take away 58.53, that will give me the size of that angle, which works out to be 121.462 ... But because it's clockwise, that implies it's a negative angle. So that means the angle is minus 121.5 degrees to 1 decimal place. Or we could say 121 degrees below the positive x direction. So question 12, we're told a skier of mass 50 kilograms is skiing down a 15 degrees slope. So part 1 involves us drawing a diagram showing the forces acting on the skier. So here's the ground, which should be horizontal. Here's the slope, 15 degrees. My skier I'm modelling as a particle, and the mass of my skier is 50 kilograms, so there's its weight of 50 g newtons. The slope pushes back on the skier with a normal reaction force like that, and the skier is moving down the slope, so let's assume there is a frictional force acting in the opposing direction like that. So these are the three forces. I haven't resolved the weight into its components at this point just yet. So part 2 says resolve the forces into components parallel and perpendicular to the slope. So that means we're looking at these directions. So that's I is parallel to the slope, j is perpendicular to the slope. So if we then draw in some components for the weight, there's a component perpendicular like that and a component parallel like that. Remember, the angle is always the same as the angle of the slope, 15. So this is 50g sine 15, 50g cos 15. So if we then look at the components, so the normal reaction force, we have 0 nr. The frictional force, now I've said up the slope is positive, so that means we have friction 0 like that. And then the 50g, the weight, we've got a component minus 50g sine 15, that's going down parallel to the slope, but in the opposite direction to positive I. And then the component perpendicular to the slope is going in the negative j direction, so that's minus 50g cos 15 like that. Now, your answers to this question will depend on the directions in which you have chosen I and j, and the question didn't specify that I had to be up the slope, it could be down the slope as your positive I direction, and so your answers may not match the answers in the back of the book completely, but they should be consistent. And I also think the answers in the back of the book have gone into I and j component form. So for example here they write this as normal reaction j, and the friction they write as frictional fi, and they also evaluate the red forces using trigonometry there, but I'm going to leave my answers as they are. Part 3, the skier is travelling at a constant speed. So constant speed immediately tells me that the skier is in equilibrium, which should be very helpful in a minute. So we've got to find the normal reaction of the slope on the skier and the resistance force as well. So looking at the forces which are perpendicular to the slope, that normal reaction acting outwards has got to be balanced by the 50g cos 15. They're the only forces perpendicular to the slope. And so if we work out 50 times 9.8 times cos 15, that gives us 473.30 ... So that's 473.3 newtons to 1 decimal place for the normal reaction. And then if we look at the forces running parallel to the slope in a similar way, the frictional force acting upwards is going to be balanced by the 50g sine 15. So if we work that out, that gives us 126.821 ... So that's 126.8 newtons to 1 decimal place. Now, in the last part of the question, the skier now returns to the top of the slope by being pulled up at a constant speed by a rope parallel to the slope. So we've got to calculate the tension force, which is going to be like that. So if the skier is now moving up the slope, we can assume that the resistance, which has the same size that it did before, is acting down the slope like that. Now, the constant speed is still the situation with regard to the motion, so that tells us that components are still balanced, the skier is still in equilibrium. So now we have tension going up, which is balanced by our 50g sine 15 plus the resistance force from earlier, the frictional force from earlier, which we calculated, and it was 126.81 ... So this then gives us the value of the tension force as 253.64 ... or 253.6 newtons to 1 decimal place. So, question 13, we have a block of mass 5 kilograms on a rough inclined plane, attached to a 3 kilogram weight by a light string which passes over a smooth pulley and is on the point of sliding up the slope. Now, there's a huge amount of information in this question, and we're going to add this in bit by bit. So we've got to draw a diagram showing the forces acting on the block. Now, the block has a weight of 5 kilograms, 5g newtons. Mass is 5 kilograms, its weight is 5g newtons. There'll be a normal reaction force acting upwards like that. There's going to be a tension force pulling up like that. And the key words here, it's on the point of sliding up. Now, if something is on the point, on the verge of sliding up, then friction is going to oppose its intended direction of motion. So the object's trying to go up the slope. That means we need to draw friction very carefully, acting down the slope. So there's my frictional force there, I'll call it F. I can also look at the forces acting on the 3 kilogram object. So there would be a weight like that, and then there would be a tension force like that. So we've got to resolve the components acting on the block into components parallel and perpendicular to the slope. So if we decide which direction we're going to take our positives, so I'm going to go with up and off the slope like that. So these are my positive I and j directions. I need to make sure I draw in some components carefully for the weight. So it should have a component like that, and it should have a component like that. And there's my angle, 25 degrees again. So then if I look at each of the forces in turn, so my tension force, first of all, that's going to be T in the I direction, 0 in the j direction. My normal reaction force is going to be 0 in the I direction, and then whatever the normal reaction value is in the j direction. My frictional force is going to be minus F, 0, and my weight, the 5g force, is going to be minus 5g sine 25 minus 5g cos 25, looking at the directions of these two components compared to the positive directions here. Now, I think again in the answers, they've evaluated the weight using the trigonometric functions on the calculator, and they may have done this in I and j component form, which is fine. So that would be Ti, this would be normal reaction j, this would be minus Fi. And then we could evaluate the weight and give it an I and j component form too. Now, part 3, find the force of resistance to the block's motion. So we've got to calculate the value of the friction. So let's take a look at the 5 kilogram block. And I'm interested in this direction here, parallel to the slope, because perpendicular to the slope, all I really know is that the normal reaction is going to be balanced by this component of the weight, and that doesn't really take me very much further in finding out the friction. So for this calculation, we know that T going up the slope is going to be balanced by F coming down the slope and 5g sine 25 also coming down the slope. So I've effectively looked at this, this and this. The ones coming down are balanced by the one going up. Now I can't go further here because I don't know what T is, so I'm going to look at the 3 kilogram block. And because this is travelling in a different direction, I'm just interested in the vertical motion here, or the vertical direction here. And all we know is that T has got to equal 3g. So this then tells me, if I go back to this equation, 3g is equal to F plus 5g sine 25. And I simply rearrange this equation to evaluate F. And this gives me the frictional force as 8.6917 ... So 8.69 newtons to 3 significant figures. So in part 4 of the question, the 3 kilogram mass is replaced by a mass of m kilograms. So what does that tell me? That tells me that over here I now have a weight of mg. This is going to have an impact on the tension here and on the tension here, obviously. And we now know that the block is on the point of sliding down the slope. So perhaps m has been reduced to the point that the other particle, the 5 kilogram force, will have a greater effect here. So if it's on the point of sliding down the slope, that tells me that my friction is going to oppose that motion by acting up the slope. So there's my friction. Draw this in green. Let's put in those components here and here again. Now the angle hasn't changed, it's still 25 degrees. That's still 25 degrees, so this is still 5g sine 25, 5g cos 25. So what do we now know? We've got to find the value of m. So if we look at the m kilogram block, first of all, again looking at the vertical components, T equals mg. And now if we look at the 5 kilogram block, again everything's in equilibrium, so all forces are balanced. This time we've got T up the slope plus friction also acting up the slope, but then they're counterbalanced by the 5g sine 25, which is also parallel to the slope but down the slope. So just to clarify, I've looked at this and this going up the slope, and they're balanced by this one coming down the slope. So I know that T is equal to mg. So mg plus my friction. Now I calculated the friction in the last part of the question. It was 8.6917 blah blah blah, and that equals 5g sine 25. So we can rearrange for mg and then divide by g to find out our value of m. And that gives us 1.2261 ... or 1.23 kilograms to 3 SF.